So today we are going to see some problems on one-dimensional motion based upon derivatives and integrals. So we'll start with the kinematic equations of motion, the derivation for the kinematic equations of motion by calculus method, and after that we'll see some problems. Okay. So we have to derive the equations known as kinematic equations of motion for that object which is moving under uniform acceleration. So we are given that acceleration is constant so we can say that dv by dt is constant and let's suppose it is equal to a. Okay, so dv by dt is rate of change of velocity with respect to time, the acceleration, and it is uniform. Okay, now the first kinematic equation is relation between velocity and time. So to derive it, we need to separate these two variables. First one is velocity and the second one is time. So let's do that. So I will write dv equals to a times dt. Okay, and this is called as separation of variables. So after this we'll integrate this equation. So as time goes from 0 to t, suppose the velocity goes from v naught to vf. Okay, so these are lower and upper limits for velocity and time. So here I can say it is integral from v naught to vf of dv can be written as integral of v raised to 0 dv, because anything raised to 0 is 1. Okay, so this is legitimate to write it like this. And similarly on right hand side, what I can do is I can take a outside of the integral because it's a constant, it does not depend on t. So this is equal to a times integral of dt, and here also I can write t raised to 0 dt. Okay, because anything raised to 0 is 1. And then we have this formula. So for example, integral of x raised to n dx is equal to x raised to n plus 1 divided by n plus 1. Okay, plus c for the indefinite integral, and if it is definite integral then we have to substitute limits. Okay, so here we have v raised to 0 dv, so integral of that will be v raised to 0 plus 1, that's 1, so v raised to 0 plus 1 divided by 0 plus 1. Okay, integral of this will be v raised to 0 plus 1 divided by 0 plus 1, that is v raised to 1 divided by 1, from initial limit v naught to final limit vf. Okay, and this will be equal to a times t raised to 0 plus 1 divided by 0 plus 1, or I can just say it is t, and lower limit is 0, the upper limit is t. Now I can substitute the limits. So substituting the limits, I get vf minus v naught, because this is just v. So we will substitute this upper limit vf and lower limit v naught in place of this v. So we get vf minus v naught equals to a times the upper limit is t and lower limit is 0. So a times t minus 0. So which can be written as vf equals to, if we take v naught on the other side, it becomes positive. So v naught plus a times t minus 0 is t. So it is a times t. Okay, so we got our relation. So this is the first kinematic equation of motion. All right. Now let's consider some time t prime. Okay. So I can say at time t prime, velocity is vt prime, and that will be equal to v naught plus a times the time is t prime. So now I will write this velocity change in position with respect to time, that is derivative of position with respect to time, but for time I am using this prime symbol. Okay, so dx by dt prime is equal to v naught plus a times t prime. Okay, my variable is t prime, and then what I will do is, now I want relation between the position at time t and the time itself. So I will separate this position and time. Okay, so I will take this dt prime on the other side of the equation. So this can be written as dx equals to v naught times dt prime plus a times t prime dt prime, and then I will integrate on both sides of this equation. So position changes from x naught to xf. So initial position is x naught, final position is xf, and time changes from 0 to t. Okay, so I am integrating the position from x naught to xf and the time from 0 to t. Now the integral of dx is just x. Okay, so this is x from x naught to xf, and here I can take v naught outside of the integral because v naught is velocity at start and it will be a constant, and here I can take a outside of the integral because a is also constant. So it is v naught times integral from 0 to t of dt prime plus a times integral of t prime dt prime from 0 to t, and this integral is simple. Integral of dt prime will be t prime, just like integral of dx is x. So this is v naught times t prime. So time changes from 0 to t. Okay, plus here we have a times integral of t dt. So it will be t prime raised to 1 plus 1, that's 2 divided by 1 plus 1. Okay, so t prime raised to 2 divided by 2, and time changes from 0 to t. Now we can substitute time. Okay, the upper limit and lower limit for the time. So we get over here, if we substitute x naught and xf, we get xf minus x naught equals to v naught times t minus 0 plus a times, it will be t squared by 2 minus 0. Okay, so we got xf minus x naught equals to v naught times t plus at squared divided by 2. It can be written as half of a times t squared. And what is xf minus x naught? It is final position minus initial position, and that is displacement. So I can write this as displacement, which we represent by s So we got S is equal to V naught times T plus half of AT squared. And this is called as the second kinematic equation of motion. Okay. So this equation is known as second kinematic equation of motion. We got first kinematic equation of motion. It is relation between velocity and time. The second kinematic equation is relation between the displacement and time. Okay. And now in third kinematic equation of motion, what we do is we establish a relation between velocity and the displacement. So for that, we start from acceleration equals to dv by dt, and then now here the variables are velocity and time. Okay, but we want relation between the velocity and displacement, that is velocity and position. So what we do is we do change of variables. Okay, and this is an important step. So what I will do is I will multiply and divide by dx. So we have dv by dt. So I'm dividing by dx and I'm multiplying by dx. This is done to remove variable t. Okay, to replace variable t with position. So now we know what is dx by dt. Dx by dt is velocity. So this term can be written as v. So we got a equals to dv by dx times v. Now as we wanted two variables, velocity and position, we got those two variables, the relation in terms of those two variables. So now we can separate them. So we can take this dx on left hand side. So doing that, we get a times dx equals to v dv, and after that now we can integrate. Okay, so now integrating this equation, we get integral of a dx, and x changes from x naught to xf. So this is equal to integral of v dv from initial velocity v naught to final velocity vf. Okay, so on left hand side I can take a outside of the integral because a is a constant. So I'm taking it outside. Then I'm left with integral of dx from x naught to xf, and that is equal to integral of v dv, or I can say it is integral of v raised to 1 dv. So that is v raised to 1 plus 1 divided by 1 plus 1, or v raised to 2 divided by 2. The lower limit is v naught and the upper limit is vf. And then on left hand side I have integral of dx, which is x. The lower limit is x naught, upper limit is xf. So this is equal to v squared by 2 from v naught to vf. And now we can substitute the upper and lower limits. So substituting them, we get a times, here we have x, so xf minus x naught is equal to, on right hand side we have v squared divided by 2. So there we have to substitute vf and v naught. So we get vf squared divided by 2 minus v naught squared divided by 2. Okay, and then xf minus x naught is final position minus initial position, and it can be replaced by displacement. Okay, so this is displacement. So a times displacement is equal to the term on right hand side. and I can take this 2 on left hand side to write it as 2 times as is equal to Vf squared minus V naught squared, or by rearranging I can write Vf squared is equal to 2as plus V naught, or Vf squared is equal to V naught squared plus 2 times of A into S. Okay, so this is called third kinematic equation of motion. So now we have derived our three kinematic equations of motion using calculus method. Now let's see some problems based upon some problems on one-dimensional motion based upon derivatives and integrals. So here is example number 2. Position of a particle is given by x is equal to 3t minus 2t cube in meters. Find its velocity and acceleration at t equals to 5 seconds. Okay, let's see what is the answer. So we are given with position of a particle, which is x equals to 3t minus 2t cube in meters, and we are asked to find the velocity and acceleration at some time t equals to 5 seconds. Okay, so we know what is the relation between velocity and position, and also the acceleration and position. So we know that velocity is derivative of position with respect to time, and for position we have 3t minus 2 times t cube. Okay, so now let's take derivative of this thing term by term. So in the first term 3 is constant, we can take it outside. So we have 3 times derivative of t with respect to t, that's 1, minus in second term we can take 2 outside. So we have d by dt of t raised to 3. Okay, then in first term we have dt by dt, that's 1. So 3 times 1 is 3, minus 2 times we have derivative of t raised to 3 with respect to t, and we know that derivative d by dx, or let's take t as variable. So derivative of t raised to n with respect to t is n times t raised to n minus 1. So here our n is 3, that's why derivative will be 3 times t raised to 3 minus 1, that's 2. Okay, so derivative is n times, that is 3 times t raised to n minus 1, 3 minus 1, okay, that's 2. So we got velocity at some time is equal to 3 minus 2 times 3 is 6, 6t squared. So this is, the unit will be meters per second because the position is given in meters. Now we are asked to find velocity at t equals to 5 seconds. So let's substitute t equals to 5 seconds in this formula we got. So we get velocity at t equals to 5 equals to 3 minus 6 multiplied by t squared, so which is 5 squared. 5 squared is 25, 25 times 3, 6 is how much? It is 150. So 3 minus 150 is minus 147. So minus 147 meters per second. That's velocity at t equals to 5 seconds. So I hope my algebra is correct. So this will be the answer. Then we also wanted to find out acceleration. So acceleration we can get by taking derivative of velocity with respect to time, and for velocity we got v equals to 3 minus 6t square. Okay, so this is velocity as a function of time. So now taking derivative of this function, so we got v equals to 3 minus 6t squared. Taking derivative, we can write dv by dt equals to d by dt on right hand side. So d by dt of 3, it is 0 because 3 is constant and constant does not change with respect to time, minus 6 times d by dt of t squared. Okay, so 0 minus 6 times d by dt of t squared is 2 times t, because we have this formula, derivative of t raised to n is n times t raised to n minus 1. So here our n is 2. So it is 2 times t raised to 2 minus 1, or we can just say it's 2t. So 6 times 2t, and that is minus 12t. That's our acceleration. And if we substitute t equals to 5, so we get acceleration at t equals to 5 is minus 12 times 5, that's minus 60, and unit will be meters per second squared. Okay, all right, then let's move on to example number 3, and it says position of a particle is given by x equals to a sine bt in meters. Find its velocity and acceleration at time is not specified. So t equals to, it's pi by 6 seconds. Okay, a is 5 meters and b is 2 per second. Let's begin to solve this. So we have x equals to a times sine of bt, and we want to find out acceleration. So we want to find out velocity and acceleration of this particle at some time t equals to pi by 6 seconds. Okay, so we know that velocity is dx by dt. So here also we have to take derivative only. So it is d by dt of a into sine of bt, and here since a is constant, I can take it outside of the derivative. So I get it is equal to a times d by dt of sine of bt. Okay, after that, now here we notice that it's not sine of t. Okay, so we cannot directly take its derivative. So what we have to do is we have to apply chain rule over here. So to apply chain rule, let's suppose u is equal to b times t. Therefore, derivative of u with respect to t will be equal to what? d by dt of b times t, and we can take b outside. So we get b times dt by dt, that is b. Okay, so the chain rule says, so let's write this in terms of u now. So we have a times d by dt of sine u. And how do we find these kind of derivatives? So we take derivative of this sine u with respect to u itself times cosine bt cos of bt times b. Okay, or I can write this as it is equal to ab into cosine bt. Okay, so I got this relation for the velocity. After that, I will substitute the value of time. So I wanted to find out velocity at t equals to how much? At t equals to pi by 6 seconds. So velocity at t equals to pi by 6 is equal to ab multiplied by cos of b times pi by 6. And now we can substitute values of a and b. So we get, substituting the values of a and b. So a is 5 and b is 2. So a is 5 and b is 2 times cosine of 2 times pi by 6 or pi by 3. Okay, so we have to find cosine of pi by 3. Now how much is pi? So we know 2 pi equals to 360 degrees. So pi equals to how much? 360 divided by 2, that is 180 degrees. So how much will be pi by 3 then? 180 divided by 3, and that is 60 degrees. Okay, so we have v at t equals to pi by 6 equals to 10 times cos of 60 degrees. And anybody knows cos of 60? I think it is half. Okay, so 10 times half, sin 30 is half, cos of 60 is half. Answer is 5 meters per second. So this is v at t equals to pi by 6. So this is answered. We have x equals to a sine bt, and we know that velocity is dx by dt. So let's substitute a sine bt in place of this x. So we get d by dt of a sine bt, and that is a multiplied by d by dt of sine of bt. Okay, because a is a constant, we can take it outside of derivatives. So now we have to take derivative of sine of bt over here. It's not derivative of sine of t. So here we have some other function. Okay, and that's why we have to apply chain rule. And what is chain rule? So to apply chain rule, we substitute u equals to b times t over here. So since u is b times t, we have du by dt equals to d by dt of bt, and b is a constant, so we can take it outside too. So we have b times dt by dt, that's 1. Okay, so b times 1 is just b. After that, we can write this as a times d by dt, derivative of sine of this function, and this function we called u, so it is d by dt of sine u. And then chain rule says that take derivative of this function with respect to this inside function, and that is u. So take derivative of sine u with respect to u and multiply it with derivative of this inside function with respect to t. Okay, so we want to take derivative of this function sine of u with respect to t. So it is derivative of sine u with respect to this inside function multiplied by derivative of inside function, that is u, with respect to t. So we did just that. So we took derivative of sine u with respect to u and multiplied it with du by dt. Okay, so this is equal to derivative of sine u with respect to u is just cosine u. So cosine u times du by dt we already found it's b. Okay, so multiplied by b. Then we substitute u equals to bt over here. So we have a times cosine of bt times b, and then we can write this as ab times cosine of bt. Okay, and then we wanted to find out the velocity at time t equals to pi by 8, pi by 6. Okay, so velocity at t equals to pi by 6 is equal to ab times cosine of b times t is pi by 6. So we substitute that, and then how much is pi by 6? So we know that 2 pi is 360 degrees. So pi is 180 degrees. Okay, it is 360 divided by 2, and therefore pi by 6 is how much? Okay, we also substitute b equals to 2. So we really want to find out what? Pi by 3. So what is pi by 3? It is 180 divided by 3, that's 60. And cosine of 60 is half. So we have 5 times 2 multiplied by half, that is how much? 10 times half, that is 5 meters per second. Okay, so we found v equals to ab times cosine of bt. Now if we take one more derivative of it, we will get acceleration. So we have v equals to ab times cosine of bt, and we want to find acceleration, which is dv by dt. So it is d by dt of ab into cosine of bt. Okay, so here also a and b are constants, we can take them outside of derivative. So we have ab times derivative of cosine of bt. So again, now we have to find out derivative of cosine of bt with respect to t. Okay, so the variable here and here are not same. Here we have some function of t. So we substitute u equals to bt and apply chain rule. So to apply chain rule, we have to find out derivative of this. So we already found it. So du by dt is b, and then I can write this as a equals to ab times d by dt of cos of u, and using chain rule I can write this as ab times derivative of cosine u with respect to u multiplied by derivative of u with respect to t. Okay, so derivative with respect to u of cosine u multiplied by derivative of u with respect to t. So this is minus sine u. So we have ab multiplied by minus sine u, and then du by dt is b. So this will be equal to minus of a times b squared multiplied by sine of u, and u is bt. So we can write this as multiplied by sine of bt. Okay, and then we wanted to find out acceleration at t equals to pi by 6 seconds. So acceleration at t equals to pi by 6 will be equal to minus of a times b squared into sine of b times pi by 6, that is minus of A is 5, B is 2. So it is 5 times 2 squared multiplied by sine of 2 times pi by 6. Okay, that is pi by 3, and sine of pi by 3 is sine of 60, and it is equal to square root of 3 divided by 2. So we get this is equal to A at t equals to pi by 6. So A of pi by 6 is equal to minus of 5 times 2 squared multiplied by square root of 3 divided by 2, and this 2 gets cancelled out with the squared. So we have minus 10 multiplied by root 3. Okay. So answer is, therefore A at t equals to pi by 6 is minus 10 root 3, and unit will be meter per second squared. So a particle is moving along x-axis with acceleration a equals to 3x meters per second squared. If it starts from rest at x equals to 3 meters, find its velocity when it reaches x equals to 5 meters. So we are given with this relation between acceleration and position of the particle. So we have a equals to 3 times x, and unit is meters per second squared, the SI unit, and we want to find out its velocity when it reaches some position. It reaches x equals to 5 meters. Okay, that means we want relation between velocity and position. Okay, so how can I write acceleration? What is acceleration? It is derivative of velocity with respect to time. Okay, so I can write dv by dt equals to 3x, but in question we want relation between what? Velocity and the position, because question is find out velocity when it reaches some position. Okay, the position x equals to 5 meters. So we don't need this time. Okay, so we replace this variable time with position. And how do we do that? So for that I will multiply and divide with dx. So dv by dx times dx by dt is equal to 3 times of x. Okay, so here I divided with dx, and here I multiplied with dx. Okay, so dividing and multiplied with dx, what do we get? So dx by dt, we know its velocity. Okay, so dx by dt is v. So we have dv by dx equals to 3 times x. And now to find out the relation between velocity and position, what we do is we separate the variables. So we have v dv equals to 3x, and I'm taking this dx on the other side. So 3x dx. Okay, and then I can integrate this. So let's see question. So it starts from rest at x equals to 3 meters. So the initial position it is 3 meters, and we want to find its velocity at x equals to 5 meters. That means we have to integrate from x equals to 3 meters to x equals to 5 meters. Okay, so let's say v naught to vf. integral of v dv is equal to 3 times integral of x dx from the initial position x naught to final position xf. Okay, so integral of this will be v squared divided by 2. The lower limit is v naught and upper limit is vf. So it will be equal to 3 times integral of this term x dx will be x squared divided by 2. The lower limit is x naught, upper limit is xf. And now let's substitute the upper and lower limits. So substituting that, we get, in place of v, we'll substitute vf and v naught. So vf squared divided by 2 minus, okay, before that, we see that we have 2 in denominator on left hand side as well as right hand side. So we can cancel it out. So it gets cancelled out and we are just left with v squared. Okay, so then we have vf squared minus v naught squared is equal to 3 times xf squared minus x naught squared. Okay, so we are given that particle starts from rest at x equals to 3 meters and the final position is x equals to 5 meters and we have to find out its velocity. Okay, so initial velocity is 0 and initial position is 3. So 3 squared, final position xf is 5. So 5 squared. Okay, 5 squared minus 3 squared and this will be vf squared minus 0 squared. Okay, so we have vf squared equals to 3 times 5 squared is 25 minus 3 squared is 9. Okay, and then we get vf squared equals to 3 times 25 minus 9 is 16. So that is 48. So vf will be equal to what? Square root of 48. Okay, so vf will be equal to square root of 48 meters per second. Plus or minus. So that's the answer.